So let's start off with some sample diploma questions from last lesson. Pretty straightforward. Which of the following types of electromagnetic radiation has photons with the greatest energy? So our formula is E equals HF, right? So our energy increases as our frequency increases. And our other formula is E equals hc over lambda. So as we increase our wavelength, our frequency decreases. So frequency is what affects the energy of it. Higher frequency, higher energy. And you have to memorize that spectrum from our very first lesson in this unit. Yeah, it was the very first lesson in this unit. You have to know that low frequency is radio, then micro, then infrared, then red light, then blue light, then ultraviolet light, then X-ray, and then gamma. So you need to memorize that order. This one has the highest frequency over here. So this is increasing frequency as we go along. So the one with the highest frequency is going to have the highest energy. So that's going to be X-ray. So A is the correct answer. And then this one we've done before, but it just asked a different question. So if I read what it's asking for, the difference in energy levels of a CO2 molecule associated with the deep dip in the SPM data. So this is the SPM data right here. And this is our deep dip with our CO2 models, or CO2 molecules. And it asked for the energy in electron volts. So this gives us a wavelength, so we can use E equals hc over lambda, right? And then if it wants it in electron volts, we have to use our 4.15 times 10 to the negative 15 electron volts seconds, multiply it by our speed of light, and then divide it by that wavelength. So it says that it's 15 times 10 to the negative 6 meters, right? So we have to find that energy. And if I calculate that energy, if I go 4.15 times 10 to the negative 15 times our speed of light, which is 3 times 10 to the 8. Sorry, I did 4.15. It's 4.14, not 4.15. So the speed of light, 3 times 10 to the 8. And then I divide it by 15 times 10 to the negative 6 meters for our CO2 dip. And it looks like we get 8.28? Yeah, times 10 to the negative 2 electron volts. So my answer would be 8282 as my final answer. Okay, so hopefully that helps. So today we're going to talk about the photoelectric effect. And so Einstein came up with the model for the photoelectric effect, and it's the only thing he ever won a Nobel Prize for. He never won it for general or special relativity or E equals mc squared, stuff you've probably heard of. The photoelectric effect is the only one that he won the Nobel Prize for. So describe the photoelectric effect in terms of intensity and wavelength or frequency, and surface material. Describe the photoelectric emissions using conservation of energy. So we're going to use physics principle 5 to do this. Describe the photoelectric effect as a phenomenon that supports the notion of the wave-particle duality of EMR. And yeah, this is just like an example. That's why it's in bold, or it's in italics, because it's an example. And predict the effect on photoelectric emissions of changing the intensity, frequency, or material for a photocathode. So you can see this frequency, intensity, and surface material are important. You need to know that. Okay, so let me explain what the photoelectric effect is. It's really easy to explain what it is. It's just harder to explain why it happens. So scientists found that when you shot light at a metal plate, you get electrons to eject from it. So you shoot light, electrons fly off. Cool. that happens, let's explain why that happens. So we have two models that we can use to explain what's happening. We have our wave model, which we call classical physics, and we have our particle model, which we call quantum physics. So with the photoelectric effect, the toughest thing to sort of get your head around is this idea of models to describe what's happening with the photoelectric effect. So what the photoelectric effect is we shoot light at a metal plate, and when we do that, electrons fly off. That's all the photoelectric effect is. So what we want with physics is we want a model to explain what's happening with the photoelectric effect. So there's two models that we have right now. We have the classical wave model, and then we have this quantum particle model. And we want to see what our predictions would be with both models. So I'm going to start with the wave model. So two things that I can manipulate are wave intensity. So intensity is how hard I make this wave go, how big the amplitude of the wave is, right? So I can have a huge intensity, or I can just have a low intensity. And the other thing that I can manipulate is a frequency. So how many waves per second? So I can have a low frequency, or I can have a high frequency. Those are my two things that I can manipulate. So to model electrons, I have electrons inside my metal plate here, and these are going to be my tennis balls. So what you can predict now and what you can see, well, let's see what happens if I have a high intensity. If I have a high intensity, you can see, oh no, my electron hit my phone. If I have a high intensity, you can see how those electrons fly off with a big speed, and we get electrons to fly off very quickly. That's what we see, right? And if we have a lower intensity, if I just do a little bit of an intensity, they still fly off, but my electrons fly off at a much lower speed. So that's what my model predicts, and my analogy keeps on knocking over my phone. So now I can change frequency, right? If I have a very low frequency, what we're going to see is it takes longer for those electrons to fly off. There it goes. But they still fly off, right? And then if I have a higher frequency, what you can see is those electrons are going to fly off much quicker. Right? Now they're off. Okay, and then some electrons are harder to get to leave because they're better bound to the metal. So now we have a harder one to fly off, right? And if I have a big intensity, well, I still can get that electron to fly off. Come on, there we go. So I can still get that electron to fly off, but it's just a little bit harder, right? But no matter what I do, I always get electrons to leave, and that's what the classical wave model predicts. No matter what light I shoot at it, whether it's low frequency like radio waves or high frequency like ultraviolet waves, it's still gonna fly off, okay? So now let's switch to the particle model. So with the particle model, we have our electrons on our plate, right? And I'm gonna represent the frequency, which is the energy, by the size of the ball. So I can have a high energy photon and I can have a low energy photon. So these electrons are relatively easy to get to leave my plate, right? So if I shoot a photon at it, I can get it to leave, right? And if I shoot a higher energy photon at it, I can get that electron to leave. But what we see with the particle model, the quantum model, is that if I shoot low energy, low frequency light at an electron that's difficult to leave, right? Nothing, right? I can't get that electron to leave.
I swear that went in the garbage can. That's actually crazy. And if I shoot a higher energy at it, right, it still can't leave. So what I need is I need a photon with enough energy to actually get it to fly off. That photon had enough energy to get that electron to leave. But what I'm doing is I'm shooting one photon at one electron, and I get that photon to fire off that electron. That's what our particle model is doing. So try to think of this when we're comparing the classical wave model compared to the quantum particle model. Okay, I hope that helps.
Watch the video. How does frequency affect the electrons being fired off? Well, what we saw in that video is it made those electrons fire off at higher speed, and we get more electrons to fire off, right? When we increase that frequency, they flew off, high speed, more electrons flew off. That's what we saw that happens. So how does the intensity or amplitude affect the electrons being fired off? Well, yeah, that one's definitely higher speed, and then more electrons. Okay, so it looks like increasing frequency or increasing intensity allows us to fire off those electrons at higher speed and have more electrons. And the thing that we saw with the classical physics is no matter what my frequency was, I always got an electron to fly off, right? If it was a super low frequency, it took a really long time, but we still got those electrons to fly off. So what we see in the photoelectric effect when we do this experiment, oops, I can't make that any bigger, is not what classical physics represents. So here's my metal plate over here, and I can shine a light on it, right? And when I shine that light on it, you can see that light hits the plate and electrons fire off, okay? And when I increase my intensity, I get more electrons to fire off. So intensity with light would just be brighter light, right? If I lower my intensity, I get less electrons to fire off, right? So intensity makes more electrons fired off, which is what we predicted with the classical physics. But I want you to take a look at the speed of those electrons. So when I have a lower intensity, and when I have a higher intensity, come on, there you go. You can see the speed of those electrons doesn't change, right? Just the number of them flying off. So this one is not correct, which is bad when you're predicting a model that it doesn't do that. Okay, and now we're going to look at the frequency. So let's take a look at the frequency. So wavelength frequency says the same thing. So ultraviolet over here is really high frequency, and infrared is really low frequency. So when I change the frequency, I'm just going to turn that intensity 100%. Nothing's being fired off. That's super weird. So nothing's being fired off. What's going on here? Oh, all of a sudden, bam, we get some electrons being fired off. I'm going to go back. Lower frequency. Nothing. Head. Oh, all of a sudden electrons fire off, right? So when I reach this sort of greenish, bluish, indigo sort of light, I get electrons to fire off. But then when I go below that level, I get no electrons fired off. That's not what our model said. And what happens if I increase the frequency even further? What changes about those electrons? Whoa, look at that. They're going faster. That's weird, right? Now they're going slower. Now they're going slower. Let's show all the electrons. So I only showed the highest energy one so we can really see that. So when I go higher frequency, oops, now we can see all the electrons. Higher frequency, they're going faster. Lower frequency, going slower. But the number of electrons isn't really changing, and that's what we predicted, right? So higher speed for sure, but not more electrons. And the weird thing was is we said that, well, no matter what frequency we had, it should fire off electrons. But when we're below the threshold here, we fire off no electrons. So that's super weird. So the classical model failed to give accurate predictions of what happens in the photoelectric effect. So what we need to do is we need to use our quantum model, our particle model, and see if that can predict it better. So when these predictions were tested through experimentation, the predictions were wrong. So what happens when I use low frequency light? Right? So when I use low frequency light, nothing happens. So nothing happens until I hit a threshold. Right? So nothing happens until I hit a threshold. Yeah, I hit the threshold and now electrons are being fired off. So remember with the video, with the model, I showed the energy of the photon as the size of the photon, right? So if these are my 3 photons of light, right, and this is my electron, no matter how much I throw this electron at it, it can't get it to leave. But if I increase the energy, oh yes, now all of a sudden I can get that electron to fire off, right? This is my photon, and these big energy photons can get this energy electron to fire off. And if I continue to increase my frequency past that point, what's going to happen is I get faster electrons, so they go faster. Right? And that's because this big photon, when it hits this electron, is going to fly off at a higher energy. It's like throwing, it's when I threw the basketball. If I threw the basketball at the tennis ball, it flies off with more energy than if I throw a tennis ball at a tennis ball, right? It flies off with greater kinetic energy. So what happens when I increase the intensity or the brightness? Okay, so here, let's slow them down a little bit, right? So when I decrease the intensity, let's switch this. So instead of showing light as a beam, let's show light as photons, right? So as I shoot more photons at it, at the metal plate, look at that. More photons release more electrons. So you can think of this as one ball releasing one ball, right? And that's kind of what we predicted. One photon can release one electron. So when I have less photons, it releases less electrons. So increasing my intensity releases more photons. So what happens when I increase my intensity, my brightness? I release, sorry, not more photons, I release more electrons. Okay. And then one thing we need to look at is what happens when I change the metal plate. So right now I have a sodium cathode is what we call it, so sodium metal plate. If I change it to zinc, all of a sudden electrons stop. But if I increase my frequency, all of a sudden I get electrons to be fired off. Well, what happens if I change it to copper? Right? I go here, nothing, 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 nothing. And then all of a sudden, bam, they're fired off with copper. So it looks like around this 174 nanometer wavelength, I can get it to fire off. And if I switch my metal plate again to platinum, there we go. Finally, I get them to fire off. So it takes super high energy light, high energy photons, calcium. There we go. I don't get them to fire off until here. So different metals. So sodium seemed to be the easiest one. So different metals have a different energy of light, energy of photon that allows electrons to be released. So they have their own work function is what we call it. So what happens when I change the metal plate is different metals have different photon energies. sorry, this is really hard to write with the mouse, energy that releases electron. Okay, so all metals have their own work function is what we call it. So the quantum or particle model worked better for explaining the photoelectric effect. So it would explain why specific quantum of energy was needed to eject electrons, and explain why one photon could eject one electron. So in this picture here, I have low frequency light, so low energy light, and I can't get those electrons to be fired off. So even when I change my intensity, I change my number of photons, they just don't have enough energy to eject electrons. But when I increase my energy, so I have higher frequency light, my 3 photons have enough energy to release 3 electrons. Okay. So like I was saying, each metal has its own unique frequency that allows electrons to be ejected, which we call our threshold frequency. And then to find the energy associated with that threshold frequency, we can use this formula. Work function equals HF, where WF is our work function, H is our Planck's constant, and F is our threshold frequency. And really this formula is just E equals HF, but this is just work function and energy HF, and this is our threshold frequency. You can also have E equals HC over lambda as well with this threshold wavelength, but it's not really a threshold because it's like a maximum wavelength that will allow electrons to be fired off, but it's the same thing. So what we need to use is we need to use our conservation of energy to explain it. So say this metal here has a work function of 3 electron volts. So if I fire an electron, or sorry, if I fire a photon at it that has under 3, I'm never going to get an electron to fire off. But if I have a higher energy photon, like 7 electron volts, then that's going to have enough energy to overcome that work function and get that electron to be fired off. So if I shoot the 7 electron volt photon at my metal with the work function of 3 electron volts, well, how much energy is this electron that's going to be fired off at? Well, think of the law of conservation of energy. So nope, I thought this was an animation. No? Oh man, I thought I had a animation. Oh, these used to move. That's super weird. Okay, well they don't move anymore. But if I fire this photon at the plate, it's going to take 3 of its electron volts to free it. So we're going to be left with 4 more. So this electron is going to fire off with a kinetic energy of 4 electron volts, right? And that's why when I continue to increase the frequency, I continue to increase the energy. Say this had 10 electron volts, and it takes 3 to fire it off. Well, I'm going to be left with 7 electron volts. And this higher energy photon is going to make my electron move faster. So it's just the law of conservation of energy. And the little formula that we use to do that, that it's not on your data booklet, but we need to memorize it, is your EK max, which is the maximum kinetic energy of our electron, is equal to the energy of our photon minus our work function. That's what we're doing right here, and it's just the law of conservation of energy, so it's not on the data book. So this is physics principle number 5. Okay, so we're going to do an example, a photoelectric effect example here. Determine the maximum speed of the electrons emitted from the aluminum surface. So it gives us a work function of the surface if the surface is illuminated with 125 nanometer ultraviolet light. Okay. So what we're going to do, oops, didn't want that one, on this one, is we're going to use this new formula where EK max, remember that this is our electron, is equal to the energy of our photon minus our work function. So we can break these formulas down depending on what they have. So they give us a wavelength. So I can break this down into HC over lambda. They give us our work function, so I don't want to break that down. And we're trying to find the maximum speed. So kinetic energy is equal to 1/2 mv squared. So I can solve for my speed. So I would just move the 2 up top, the mass down below, and then square it. So remember that this is an electron, so this mass is an electron mass. So let's plug in numbers. Okay, so we have some problems here. When we use EK equals 1/2 mv squared, this is in joules, right? Because a joule is equal to a kilogram meter squared per second squared. That's what a joule is equal to. So if we're ever trying to find speed, we need to be in joules. They gave us the work function in electron volts, so we're going to have to make a conversion. So they said that the work function is 1.08 electron volts. So what we need to do is we need to switch our electron volts into joules. And 1 electron volt is 1.6 times 10 to the negative 19 joules. So if we go 4.08 times 1.6 times 10 to the negative 19, we get 6.528 times 10 to the negative 19 joules. So now everything will be in joules and it'll work. Okay. And as you do more of these problems, you'll see when you can be in electron volts and when you can be in joules. So I want to use my joule H, so 6.63 times 10 to the negative 34 joule seconds, speed of light, divided by my wavelength of 125 nanometers. And I want to subtract this work function, 6.528 times 10 to the negative 19 joules. And I want to take this whole thing, divide it by 2, and then divide it by the mass of the electron that I'm firing off. And remember, that's on your data booklet. Okay, and we need to square root it to finish it off. So I'm going to use my on-screen calculator, so I'll show you how I type this in. So I do all this stuff in brackets. First, I'm going to double bracket to start. So 6.63 times 10 to the negative 34 times the speed of light. So that's my top. And then my bottom is 125 nanometers. Okay, and then I'm going to subtract my 6.528 times 10 to the negative 19. Close my other bracket. Oops. Let me show you how to do it. And then I screwed up. Sorry, I don't need a bracket at the end of this. There we go. And then I want to multiply that by 2. And I'm going to divide that by the mass of the electron. And then I'm going to square root my answer. And that's the wrong answer because I can't be times 10 to the 11. What did I do wrong? Oh, 125 times 10 to the negative 19. Oops. If I push second enter, second enter, second enter, second enter. I was just showing you that if you're ever faster than the speed of light, well, an electron can't go faster than the speed of light. So that's how you know you got a wrong answer. So let me switch that. Sorry, I read that wrong. And then multiply that by 2. And then divide that by 9.11 times 10 to the negative 31. And then square root my answer. And I get a much more reasonable answer. I get that my speed of my electron is going to be 1.43, 1.44 times 10 to the, and it can't be bigger than 8, so 1, 2, 3, 4, 5, 6, yeah, times 10 to the 6 meters per second. Okay. Sorry about that. Okay, so let's try some board questions with that. So take a read, pause the video, write it down on a piece of paper, see if you can do it, and I will go through it right now. So find the wavelength of light that caused electrons to be emitted with a speed of 8.17 times 10 to the 5 meters per second when the work function of the metal is that. Okay. So we're going to use our formula. EK max is equal to our energy of our photon minus our work function. Okay. We want to find the wavelength of light. So we're going to break this down. We're trying to find that. It gives us the work function. Oops, I don't want to write that in yet. And it gives us the speed, so we'll break this down into 1/2 mv squared. Right, so first thing I'm going to do is move the work function over here. And then I can move my wavelength up top. And then I can move both these guys down below. So I would end up with wavelength is equal to hc over 1/2 mv squared plus my work function. So wavelength moves up, those guys move down below. Okay. Again, because speed is involved, anytime speed is involved, you have to be in joules. So I'm going to convert my 2.12 electron volts into joules, and 1.6 times 10 to the negative 19 joules equals 1 electron volt. So 2.12 times 1.6 times 10 to the negative 19 is 3.392 times 10 to the negative 19 joules. Okay, now we are ready to plug into here. So 6.63 times 10 to the negative 34 joule seconds is our h, speed of light, divided by 1/2 mass of the electron. And our speed in the question, which is 8.17 times 10 to the 5 meters per second squared, plus this work function of 3.392 times 10 to the negative 19 joules. Okay, so again, it's a big calculation, so I'll use my on-screen calculator to type that all in. Yeah, I think I can do this all in one. Let's put a double bracket to start just in case we need it. No, we don't need a double bracket to start. We just need our top. So 6.63 times 10 to the negative 34 times the speed of light. And then on the bottom, yeah, we have to double bracket the bottom. So 1/2 times 9.11 times 10 to the negative 31 times 8.17 times 10 to the 5, and I just want the squared to be on that. So I want to do it inside the bracket right after my scientific notation, and then I want to add that on to 3.392 times 10 to the negative 19, and then close my bracket on the bottom, and I get that, which looks to be about 309 nanometers. Okay, so hopefully you got that answer. And again, if you have any questions, just let me know, and I can email you, I can Google Meet you, and I can help you with that, whatever you need help with. Okay, so we got one more board question, just because this is a trickier concept, so pause the video, try it out. Find the threshold frequency of a metal when UV light with the frequency of that is fired on a metal plate and electrons are ejected with the kinetic energy. So for this one, because we're not dealing with speed, we don't actually need to be in electron volts, right? So we're trying to find the threshold frequency. So work function we can break down into this. We want to find this. And they give us a frequency. So this is HF of our photon. And they gave us a kinetic energy. So we don't want to break this down because they don't give us a speed, they give us a kinetic energy. So to rearrange this, I'd throw HF, I'd minus an HF, and then I get EK max minus HF equals negative HFO. And I'll just get rid of the negative over there by making this negative, this positive, and then I can throw my H underneath like that. And that's how I find my threshold frequency. So I can be in electron volts for this one. So negative 2.13 electron volts plus, I'll use my H in electron volts. And my frequency, this is my frequency of my photon, which is 1.43 times 10 to the 15 hertz. And then divided by my h. Again, in electron volts, I want to stick with that electron volt seconds, and I can find my threshold frequency. Oops. Opposite of what I wanted to do. There we go. On top, I'm going to go negative 2.13. I'm going to add it to 4.14 times 10 to the negative 15 times 1.43 times 10 to the 15. Yeah, just double checking it. And then I'm going to divide it by 4.14 times 10 to the negative 15. And I get, that is my threshold frequency. Wait, what? That's the same as my frequency that I shoot at it. That doesn't make sense. Oh man, sorry for all the mistakes. Let me just try that one more time. Or let me break it up into smaller ones. So negative 2.13. Oh, 2.31. Aha. Man, sorry, little mistakes. 2.31. There we go. Copied that down wrong. So that makes... Why does it still get the same answer? Okay, let me do this in smaller chunks. So negative 2.31. Sorry, these are like on the spot and I can't edit these after. Plus 4.14 times 10 to the negative 15 times 1.43 times 10 to the 15. Okay, divided by 4.14 times 10 to the negative 15. Oops. There we go. That makes way more sense. So I end up getting 8.72 times 10 to the 14 hertz. You probably all see what I was doing wrong the first time, and you're like, don't do that. Okay. Yeah, sometimes breaking these into little chunks makes it a little bit more manageable. So that's our threshold frequency, which should be less frequency, lower number than what we got. Okay, glad we could get an answer there. Okay, what's our video at? We're already at 30 minutes. So what I'm going to do is I'm going to stop the video here, and I'm going to finish this tomorrow because from the feedback, people didn't like long videos, and I don't like long videos either. So I'm just going to stop this here and then record the other video tomorrow and send it to you. But you can do some of the homework. Oops. So the homework that you can do is, photoelectric effect calculations. So you can do this and this. So these two you can do right now, and then the other two I'll finish up tomorrow. So do those two for homework, and let me know if you have any questions. Okay, are you guys ready for day 2 of the photoelectric effect? So we're just going to add on just a little bit to this. So what we're going to see is we're going to see EK max versus frequency graphs, or something along those lines. So I'll show you how to analyze EK max versus frequency graph. This is what they'll look like here. So find Planck's constant, the work function, and the minimum threshold frequency. Okay. So what we need to do is we need to use our formula we learned yesterday that's not on our data book. So EK max equals the energy of our photon minus our work function. Okay, so I'm just going to break this one down into HF. So I'm just going to break that one down into HF. And what we need to do is we need to analyze this graph in terms of y equals mx plus b. Right? So in this graph, our y value is our kinetic energy of our electron, and this is already rearranged quite nicely. Right? And then our frequency of our photon is our x-axis right here. So our x-axis is that photon. So what we see here is we see that our slope is equal to h. Really nice and easy, right? And instead of saying plus work function or minus work function, I'm just going to say plus negative work function. So our b value, our y-intercept, must then be equal to our negative work function, right? So that's really easy. So if we wanted to calculate the slope of this graph, oh, look how straight that line was to start. That was pretty good. And then we'll use this point here. So this will be our 1, and then this will be our, oh, this wasn't as straight there. That'll be our 2. So we can find the slope of this graph, and if everything is done right, then we should be able to get Planck's constant from that. And because we're in joules for our kinetic energy, our answer is going to be in joules seconds. Okay, so we should get the 6.63. So if we find our slopes, we go y2, which is 4 times 10 to the negative 19, because that's the units here, joules, minus 0, divided by our x, which is 10, and the units are times 10 to the 14, minus 4 times 10 to the 14. We get 6.67 times 10 to the negative 34. And the units would be joule seconds, because in our y we have joules, and then hertz is 1 over seconds. So 1 over 1 over seconds would be joule seconds. So yeah, pretty close, right? 6.63, 6.67, good enough. And then our work function would just be, so if we move the negative over here, if we go negative, looks to be about, I don't know, 2.1, or no, it's not 2.1, 2.6, because this would be 2.5, 2.6, so negative 2.6, but it's not 2.6, so our work function is going to be, so that those negatives will cancel out, it'll become positive 2.6 times 10 to the negative 19 joules, because you have to remember this. So that's our work function. Okay, and the last one it asks for the minimum threshold frequency. So our threshold frequency, if we just hit our threshold frequency, that'll make our EK max to be 0, right? If we shoot a photon at our metal plate with just enough energy to release that electron, right? Just enough to equal that work function, then our EK max is going to be 0, right? So if this is equal to 0, then what we can say is that HF is minus our work function, which I can break down into HF naught, right? HF 0, like that, and move this to the other side. Our HF of our photon is going to equal the HF of our threshold frequency, right? So what that means, what it comes down to, is where EK max equals 0, where this hits the x-intercept, this is our threshold frequency right here. So if you just find the x-intercept, our threshold frequency is going to be roughly 4 times 10 to the 14 hertz. That's going to be our threshold frequency. Okay, so that's how you can find all those values, and obviously I'm going to test you on that. So you gotta know how to do all those. Okay. So other graphs you might see is a photocurrent as a function of intensity. So let's bring back our simulation here. So the first one is photocurrent. So photocurrent, these electrons that are released are called photoelectrons. So photons hit our plate and photoelectrons are released. And you can see we get a current because we have a charge passing a certain point in a certain amount of time. So remember that current I is equal to charge per time. So the more charge we have, there we go. The more charge we have, the more current we have. And that's exactly what intensity does, right? When I lower the intensity, I lower the number of photons hitting the plate. And if less photons hit the plate, less electrons are released. So you can see that we have a lower current. So if I increase my intensity, more photons release more electrons, which means more current passes this point every second. So what we get is we get a direct relationship when we do current versus intensity. And let's call that current just because that's confusing with I and I. So our current increases when our intensity increases. So if we do photocurrent as a function of frequency, well, what we're going to see is that, right, when we go below that threshold frequency, we don't release any electrons, right? So nothing, 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 nothing. So here I'm increasing my frequency, nothing, 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 nothing like that. So we can show that on this graph here. So this is current and this is frequency. So we're going to see nothing, 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 nothing. And then all of a sudden, what we're going to see is we hit that threshold frequency, and all of a sudden, electrons are released. So we're going to see this spike, and all of a sudden we have a current when we hit that threshold frequency. But as we continue to increase our frequency, right, take a look at what happens to the electrons. So we increase our frequency, and those electrons are just going by faster. So just because they're going by faster doesn't mean that we get more of them. To get more current, we need to have more charge. We don't need faster charge. So what we see from this graph is we see a flat line, is that after we reach that threshold frequency, the current's going to stay the same because they're just faster. There's not more of them. Okay. So intensity increases the number of electrons released, which would increase the current. Frequency makes the electrons go faster, but our current is going to stay the same. So another thing that you need to know about is v-stop. So Robert Millikan, the same guy who found the charge of an electron, in his Millikan oil drop experiment, he applied a back voltage to make those electrons stop, right? So remember, those oil droplets, they'd be vertical like this. So those oil droplets drip down, but then what he did is they were all negatively charged, is he made a positive plate and a negative plate, and it caused those electrons to either accelerate up, down, or it could cause them to stop in between. So this is the same sort of thing, and the way that he did that is apply a back voltage. So all you need to do to create a back voltage is hook a battery up to your plates, and it might be hard to see, but this side is positive, this side is negative, and then let's lower the number of electrons so you can see it a little bit better. You can see that they release this way and then they go backwards. So if you applied the right voltage, you could actually get those electrons to stop. Let's show only the highest energy ones. So I can get it to stop. It's hard to get it stopped. You kind of have to go this way, go this way, this way, this way, and then you gotta get them to stop in the middle there. So eventually they will stop in the middle there. I kind of got that one to stop. So you just apply a back voltage, right? And he found that the voltage required to exactly stop a photoelectron and use this to find energy, right? So as these electrons are released, so we have electrons being released, they have a whole bunch of EK, right? Those photons give them energy. They have a whole bunch of EK and they spit off of there. But what he made them do is he made them stop. So if I make this plate negative and this plate positive, right, it's going to eventually slow down, slow down, slow down to the point of stopping. And when it stops, it has electrical potential energy. So we already did this. We did this before, and this is a law of conservation of energy, where my kinetic energy here is going to equal my electric potential energy. And we broke this down before to be VQ, right? And this is just the max kinetic energy of our photoelectrons, right? And then this is how we get this formula down here. And this formula, it's a law of conservation of energy formula, but it is on your formula sheet. It's just right there. It's all under atomic physics. So it's the very bottom left one. So we've now used the 3 of these in atomic physics. I don't know why they're in atomic physics. I think that's a bad title for it, but it is the title for it. So we've used those 3 there. Okay, so photocurrent as a function of stopping voltage, right? Okay, so if we go back to the simulation, let's show all the electrons being released, and let's put our current at 0. So when our current is 0, when our voltage is 0 on our battery here, we get a current, and as we increase that back voltage, our current goes down until it eventually stops. So as I increase my voltage, my current goes down. So what we see is we see an inverse relationship. So current as a function of voltage, it's going to have an inverse relationship like that. So you can see any of those graphs on there. You can memorize them or think them out, whatever you want to do. Okay. So let's do an example. Determine the stopping voltage of an electron with 3.1 electron volts of kinetic energy. Okay. So let's do this. Oops. So all of this, if it's a photoelectric effect question, almost exclusively you start it with this EK max equals our energy of our photon minus our work function. Okay, that's what pretty much all of them are going to start with. So normally we could break this down into, we had the option of breaking it down into 1/2, is that still on the screen? Yes, 1/2 mv squared. But now with this new formula that I just showed you, we can also break this down into VQ. So we have 2 options to break this down into, and we're trying to find the stopping voltage, so we're going to break it down into VQ. So just a new thing to break it down into. They give us, determine the stopping voltage of an electron with 3.1 electron volts of kinetic energy. Oh, shoot, sorry. I was doing the next problem with this formula. Sorry, for this one we just need EK max is equal to VQ. Sorry about that. Yeah, this is one of the shorter ones. So they give us the kinetic energy, and we want to find the stopping voltage. So the reason I do this question, it's a simple question, is because I want to talk about electron volts and joules. So if I am in electron volts, one thing I can do is I can switch my electron volts into joules, like that. And if I go 3.1 times 1.6 times 10 to the negative 19. I get this. So now it's in joules. So if I want to find my voltage, I could just do that. So my EK max is 4.96 times 10 to the negative 19 joules, and then I divide it by 1.6 times 10 to the negative 19 coulombs, because that's the charge on the electron. And when I do that, I get, magically, look at this, I get 3.1 volts. Okay, that seems like a waste of time, because what I'm doing is I'm taking that 3.1 and I'm multiplying it by 1.6 times 10 to the negative 19, and then I divide it by 1.6 times 10 to the negative 19, and I get 3.1. So what you can do in order to not be doing useless steps is, if your EK max is in electron volts, what you can do is you can just get rid of this Q. If we have 3.1 electron volts of energy, then it's going to take 3.1 volts to stop it. You can just get rid of that Q. And I think that's what we can do in the next question here, which I thought we were doing first. Yeah, so this is a big photoelectric effect question. So light with a wavelength of 300 nanometers is directed at a photoelectric surface that has a work function of 2.6 electron volts. Determine the stopping voltage needed to reduce the current to 0. Okay. So we're trying to find voltage. So I'm going to start with this. This is what we had before. So my EK max I can break down into VQ, and they give me my wavelength, so I can break this down into HC over lambda, and they also give me my work function. So when you have the formula broken down like this, and it's asking for the voltage, if we make sure our H is in electron volts and our work function is electron volts, everything over here is in electron volts, what we can do is we can just get rid of that Q. And it makes it much easier to work with, much easier to rearrange. And you should do that. Okay. So our H is going to be 4.14 times 10 to the negative 15 electron volt seconds times the speed of light. And our wavelength is 300 nanometers, so 300 times 10 to the negative 9 meters. And we subtract our work function, which is 2.6 electron volts. Okay, and if we plug this in, redeem myself from last lesson. It's right in the middle there, so I'm going to do it in chunks. 4.14 times 10 to the negative 15. And I multiply that by the speed of light. And I divide it by our wavelength of 300 times 10 to the negative 9 meters. So this is my energy of my photon. Oh man, made a mistake. I have trouble with this on-screen calculator, sorry. I did times 10 to the negative 19 instead of times 10 to the negative 9. 300 times 10 to the negative 9. That was a ridiculous amount of energy. So 4.14, makes way more sense. So I subtract 2.6, and our voltage to stop it is going to be 1.54. So our V stop is equal to 1.54 volts. Okay. So if you're in electron volts and you break down this into VQ, just get rid of the Q, and you don't have to do as many conversions and things like that. Okay. Okay, so this is the science behind this is how solar panels work. So the photoelectric effect is the science behind solar panels. Light causes movement of electrons, which can be used to charge batteries, right? So your sun shines on your solar panel, which is a photoelectric surface. It releases electrons, and those electrons would charge your battery. And this is how you could set up. I actually set up a solar panel system on my shed to charge some lights, and I have an outlet in there now, so you just have your solar panel that goes to your charge controller, and that charge controller just makes it so that your battery doesn't overcharge, or it doesn't drain your battery completely, because it's bad for that. So the charge controller charges your battery system. And then if you want to plug stuff in, you need an inverter because batteries work on DC power, and then everything that plugs in is AC power, so it just inverts it to AC. And yeah, you can run stuff off of a solar panel system really easy. Okay, so this is your homework. These are the EK max versus frequency graphs, and these are the stopping voltage questions. So give that a go. This is it for the week because Friday's a PD day and Monday's a long weekend. So you have all weekend to work on these questions. And then next week we'll do Compton effect, and we'll do a quiz, our last quiz in this unit, and then we'll start our new unit. So yeah. So give those a go and send me an email if you have any questions, and we can chat, we can Google Meet, we can do whatever you need. So just let me know.